Thank you for the opportunity. And let me start by reiterating Patrick's point that it's certainly not too late. It's just at the right time to start thinking about contributing your data or results from your data for our study of fluoroquinolones and their associated risk with aortic aneurysms. I have to say, in terms of contributing data, just today we got approval from the U.S. Department of Veterans Affairs to release their results for this study. And as you might expect, fluoroquinolones are very popular antibiotics amongst our veterans here in the US. And our veterans in the US sure have a huge number of aortic aneurysms. So it should be very helpful for helping to, or aortic aneurysms, right? The question is the intersection, or down with that. The question is the intersection between the different exposures and the outcomes. So please continue to work. If you need some help with executing the strategist tools for both the cohort method and self-controlled case series, I've gotten over a couple of big bumps that I can help your data sources with as well. Today, as Patrick mentioned, I'm going to discuss evidence synthesis, or ideas for combining evidence that we have across multiple data sources across the community, and in particular, a focus on utilizing as much as we can the evidence that we get from some of our smaller data partners to aggregate that information to provide the most extensive and reliable estimate possible. We're all very familiar that we're running the SOS challenge across a distributed network, which includes many of us as different data partners across many different types of healthcare systems. Across many of these healthcare systems or data sources, the important thing to remember is patient-level data itself almost surely cannot be shared. And so that introduces a number of difficulties when we want to generate aggregate evidence across many different types of data sources and healthcare systems. The way that we've been executing is, you can think of one site, in this case, this is University of Adelaide, as a study lead, and they have developed analytic code that we'll talk about later in terms of executing, that was developed kind of locally, and then this code is then distributed across all of our different study participants, like the US Department of Veterans Affairs. The results within these firewalled areas are then generated, and only aggregate statistics can be shared so that we don't violate patient privacy or ownership issues of the patient's information. And these results are sent back to the lead study, and we'll talk about how this aggregated information can be brought together today. This principle across a distributed research network was, as far as I know, first demonstrated in this paper that I've listed here. Lead author was John, looking at the risk of angioedema associated with several different treatments for seizure prevention. And we were very happy to celebrate that we brought together data from 6 different heterogeneous data sources to construct a single meta-analytic summary estimate. But our enthusiasm of this success hides a bit of our failure as well. If you read the if you move past the abstract of this brief communication into the details, you might realize that we actually had executed across 10 different data sources, but yet our summary results included just 6 of them. And so we need to talk about why we weren't able to include information from all of our data sources across an equal footing in generating this aggregate statistic. And the primary reason why we had to throw out information from patients and their lives, sorry, hold on, forgot to turn off my phone, my apologies. Why we had to throw out information from patients and their healthcare experiences relates back to the types of summary statistics that we tend to share across these federated data sources. In general, within a data source, will fit a Cox proportional hazards model, which allows us to estimate within that data source something like the relative risk of the outcome between the two different exposure groups. And we generally assume that this hazard ratio is normally distributed. So all the information that we need to know about the hazard ratio can be subsumed into a point estimate, sort of a central tendency of this normal distribution, and a width or a standard error, and that there's no additional information that our patients provide. Unfortunately, in many of our observational studies across our network, this hazard ratio is only poorly estimated as a normal distribution. And here on the slide is sort of an example of what the likelihood function looks like, centered around the hazard ratio, centered very close to 1, for a real data example in a relatively large data source. And in the dashed lines, you kind of see the normal approximation that we would be assuming. And you can see that, yeah, maybe it fits the central tendency okay, but it certainly doesn't tell us really about how far in the tails we should actually consider this estimate to be reliable. And this actually happened to occur when there were both a reasonable number of outcomes, both in the target and the comparator cohort. However, the situation gets even worse when the number of outcomes is 0 in either the target or in the comparator cohorts. In this case, the likelihood function as a function of that hazard ratio doesn't even form a curve, meaning form a curve with a mode, but yet it's monotonic. So it continually decreases over time. So whereas it doesn't give us information about what the most probable hazard ratio is, it does still provide information that we'd like to use about, in this case, an upper bound, or in the case when these outcomes might have been shifted, it's monotonic the other way, and it tells us about the lower bound. So ideally, we'd like to be able to control for both the non-normality in our estimates across data sources and not have to throw out data sources where the likelihood ratio is still informative, but yet is monotonic. So the solution to these two problems comes down to a couple of key ideas that we'll talk about today. The first is data sites are going to share the actual or an approximation of the likelihood function itself, instead of just the point estimate of the maximum likelihood estimate for the hazard ratio and the confidence interval. So we will share that non-normality information. And the way that and the idea that you should keep in the back of your mind is in statistics, there's something called the likelihood principle. And the likelihood principle states that you gain all of the information from the data that is possible from the shape of this function. Generally, we're throwing some of that data out by saying, oh, we think this function is normal, and we only need to know about the sort of the central tendency and its skew. And then we'll be able to build a single model over these likelihood shapes using a Bayesian random effects model. So we'll talk both about the approximation of the likelihood function and its sharing and Bayesian random effects modeling. We're going to start with kind of some simple ideas on Bayesian random effects modeling as an extension to the standard analytic model. So the standard meta-analytic model. The standard meta-analytic model says that each of our point estimates are drawn from a normal distribution centered around an estimable population level average that we can think of as our summary for our meta-analytic estimate. And it occasionally allows us to estimate, depending on the type of meta-analytic model, sort of dispersion around that central tendency. How much might we expect each data source on average to differ from all other data sources? So the Bayesian random effects model makes the same other assumptions. We're going to assume that we have some likelihood function that describes our hazard ratio. That hazard ratio is, drawn, that the unknown hazard ratio itself is drawn from a normal distribution with a mean that will estimate mu and its standard deviation. We'll have to make some assumptions about what the standard deviation looks like depending on the number of databases that we have. Often this variance is hard to estimate when the number of data sources is small. And by small, I really mean on the order of like 10. That is a small number for estimating the variance of a normal very well. So in many cases, making some prior assumptions about what that variance looks like is actually going to return a more efficient estimate of the true population average than the standard analytic model that makes no prior assumptions on it. So some assumptions that we could make is that tau is 0. There actually is no heterogeneity, and we have a fixed effects model. Or we could compute the relative probability that tau is 0 versus not 0 to ask us how much do our data provide evidence to reject a simple fixed effects meta-analytic model. Or we can put other distributions on them as well. Once we've made these prior assumptions, we can fit our Bayesian model, which takes as input these likelihood functions and prior assumptions about our two unknown parameters, and uses something called Markov chain Monte Carlo to estimate the posterior distribution of our quantities of interest. What is our meta-analytic point estimate, and what is the dispersion around that point estimate to develop some sort of confidence or credible interval. Now, fortunately, so many of you don't know that Odyssey is really a part-time job for me. And in reality, my real job is running a community that has spent about 20 years developing a very efficient Markov chain Monte Carlo engine. So I'm quite happy that this is a great opportunity for me to combine my real job with my Odyssey hobby for once, and hopefully there'll be more opportunities for that in the future. But we already have the tool stack across the community to fit these types of models, so we have a leg up. We'll use Markov chain Monte Carlo through this beast engine basically to simulate from the joint distribution of what our unknown population level effect estimate is and how much we expect each of our data sources to vary from that. And these are just different types of output that you get from a Bayesian analysis. Notice that under the Bayesian approach with our sparse data, our estimates no longer need to be normally distributed, but can have very interesting features, like this one here, which suggests some sort of multimodality in mu, meaning across our populations, there really might be a couple of different effect estimates. Where some data sources support one effect estimate, some other data sources affect another. And in the future, this will allow us to help dissect that type of heterogeneity. So model extensions will allow us to move not just to sort of patient level heterogeneity, but data source level heterogeneity as well. So let's return to what those likelihood profiles look like in the initial in our initial work looking at angioedema. Remember that we had started with 10 different data sources, right? But 4 of those data sources had monotonic likelihood functions. So we weren't able to report the point estimate and the confidence interval. And in constructing our hazard, our meta-analytic estimate, we had to throw out all of that information, where you can see that it actually provides a little bit of information about where the tail is. So here's sort of the meta-analytic estimate that you would get just using the data sources that we could using our sort of the standard approach using likelihood profiling, we get more information. We actually see that the hazard ratio itself, a better estimate for it, is actually a little larger than 2 because of these bounds that we had. So let me remind you of kind of these key ideas. We're going to first directly approximate the shape of this likelihood function within each of the data sources. And then instead of just communicating a point estimate and a confidence interval, we're going to communicate the whole shape of that likelihood function itself. There are a number of different ways of approximating this likelihood function. And my dear friend Martijn Schumi spent a whole lot of time sort of developing a number of different approximations, including, sitting down and thinking really hard about what a good functional form might be. He then came to me and said, hey, I have these great approximations. And I was like, that's fine, but we could actually just evaluate the likelihood at a number of different grid points and not have to rely on any of the, on any of this careful thinking on what the function might look like. We'll just let the data tell us what it is. And then we can compare how well we perform. It turns out that grid-based approach, where we're just going to evaluate the likelihood function for the hazard ratio at a number of different grid points over a reasonable support, returns much better performance than any of sort of the custom function building that we had attempted beforehand. And the reason being is the zero counts, that monotonic likelihood function is not very well approximated at all by any finite distribution. And the way to think about that is it's monotonic. It doesn't integrate to 1. It can't be a standard distribution itself. So best practices now are to use an adaptive grid. So we start evaluating the likelihood function. We ask how well does our current approximation fit unsampled points. If it's fitting it well, that's a good grid. If it's not, we continue to add more grid points until our error is sufficiently small. And then that likelihood function gets, or at least the evaluation of that likelihood function, a number of different grid points, gets shared back with our study lead. And that kind of begs a question of, when do we calibrate based on our negative controls? And you can think of it being kind of 2 choices, right? Within a data source, I might calibrate my estimates for those negative controls, right? And then send sort of the likelihood function, if one kind of existed, of that calibrated estimate back to our study coordinators. So basically you're calibrating once per data source. An alternative approach is calibrating many times. So for each of our possible negative control outcomes, we fit a separate meta-analytic model. Then once we have different meta-analytic estimates for all of our negative controls and our outcome of interest, then we do 1 round of calibration based on those meta-analytic answers. And it turns out that that's probably best practice because it helps account for sort of the non-independence between the sources of confounding across data sources. Right? If all of our data sources had the same confounding, which we weren't really capturing with our negative controls, then if we calibrate within a data source, we don't learn that we're missing it across all of our different data sources. We think we've calibrated correctly and gotten rid of all the residual confounding. And then as we add more and more data sources, our meta-analytic estimate, because we think we got it right in the first place, is going to shrink down to an overly small confidence interval that doesn't account for that non-independence. So just as kind of a refresher, this is a slide that Young just put together for me, and I liked it a lot, but I didn't have a good opportunity to really work it into the talk. Is kind of looking at these two options, so it's kind of clear in our minds, right? The first is within a site, we get an estimate of interest and a whole bunch of negative controls, and we perform a meta-analytic estimate within that site, to get our the hazard ratio for our outcome of interest. And this is kind of done independently from site to site, ignoring the dependence between the confounding structure possibly within these different data sources. Option 2, which is currently preferred. Oh, now I'm having right. Is to return the likelihood profile for all of our negative controls back, and then at a single point run a meta-analysis for each of the different negative controls across all of the sites, and then do an empirical calibration to account for that non-independence and the residual systematic error. And I suspect now the third time one of us gives this talk, we'll actually get that right. So please ask questions, which I'm sure you'd have for that horrible description.
Well, Mark, maybe just to go back to that picture, because I think there is one part that's probably not intuitive, or at least is not intuitive for me, because we oftentimes talk in the community about the fact that we think calibration is super important for a given source. Mm-hmm. And so if you are producing just an estimate within your own database, that's effectively option 1, in that you are a given site, and the goal would be do the calibration of the negative controls so that you have a calibrated estimate at your site. And so, and still, like when we communicate, what have we learned from a collection of sites? We want to get those calibrated estimates from each of the sites, because that's the best answer for a given site. But what we're talking about here in option 2 is we want to produce the best possible meta-analytic estimate. And that's why we kind of have to reorient this to basically say, what is the bias that is existent across the sites, and how do we incorporate that into our analysis? So that's why we, even in a future state, we would be in a situation where we would show calibrated estimates from each of the sites. That would be kind of look like option 1, but then the meta-analytic estimate would be this synthesis and then calibration, which would be option 2.
That's great. As I predicted, the third time we went through this slide, it would be done correctly. Thank you, Patrick.
In many cases, we do not have the negative control outcomes in several databases, since we picked that negative control outcomes, which is relatively rare conditions. So even though the databases will have the results for the primary outcomes, so what happens if some databases does not have the negative control outcomes, but they have the outcomes for results for the primary outcomes?
Right. So that this is another example where when you're looking for a meta-analytic estimate or a best guess across that, where option 2 is a good direction to go, right? Because without the negative control estimates within your own data, without sufficient negative control estimates within your own data source, it's hard to adjust for that residual system on the negative controls is an uncalibrated estimate within that data source. However, once you share all of that uncalibrated information about your effect estimate of interest and about what negative controls you do have, you can continue to assume exchangeability with negative control estimates from other data sources. So in effect, you get to capitalize on the distributed network, not distributed, but the network aspect of our community to pool that information. So you can continue to participate and get a calibrated meta-analytic estimate from your data source. So thank you for raising that, Chan. That continues to be a difficult conundrum that we face. The choice of, how choices of negative controls should or shouldn't differ from data source to data source. In many cases, I don't know what the correct answer is there. There's a lot of results on this page. I basically just put it up to say, yeah, we wrote a paper and we studied the properties, and in general, it tends to work pretty well. Let me just focus you on the kind of random effects Bayesian meta-analysis, which is the approach that we're looking at the moment. We'll look at sort of, custom or grid, doesn't really matter, sort of the grid results. These are going to be, they worked really well. And then the traditional approach, which is I took the point estimate and the 95% confidence interval from each data source and ran a standard meta-analytic answer. And if you look at bias, you want bias when you know the truth to be really small. And so for the Bayesian random effects model using these profiles, it's nice and small. And of course, with the traditional approach, it's really big and nasty. Likewise, you want, nominal operating characteristics, like I'd like my coverage to equal what my purported type 1 error rate is. Using the new approach, covers about 95%, but coverage is much poorer using kind of the standard approaches. And you can go across different estimates as well. Mean squared error, percent non-estimability, right? We have to throw out a lot of information. We throw out too much, we're left with nothing. So the moral of the story is it tends to work pretty well. We now consider it best practices in the community.
Mark,
so let me, go ahead, please.
I have another question about.
Absolutely.
I'm a little bit confused between the fixed effect or the random effect Bayesian meta-analysis.
Okay.
Since you introduced that, you will assume the heterogeneity as 0.5 for the random effect Bayesian meta-analysis. Am I correct?
Help me understand the 0.5. 0.5 for what?
About the heterogeneity between the results.
Okay, so a fixed effects analysis says there's one unknown effect estimate, which is the best effect estimate in each of the data sources, and they're all equal. And you can estimate what that single effect would be, and it should be the best estimate within each data source and across. A random effects model says that the best effect estimate within a data source can vary from data source to data source, but they're all drawn from a common distribution. And that distribution has a center point, which we would call our best meta-analytic estimate, right? If you were to give me a new data source and ask, what do I think the hazard ratio is in that new data source, or a new patient who isn't included in any of the data sources that we've looked at, then that point estimate would be the best place to look. You can certainly do model selection. So ask, given the data that we have across all data sources, what's the relative probability of a fixed effects versus a random effects model if you are concerned that the random effects model might be over parameterizing things. The easiest way to look at that is to fit a random effects model and look at the posterior distribution of that tau, the spread or the variance parameter, and ask, does the posterior look like 0 is kind of a reasonable value? Because our prior said 0 was kind of a reasonable value. If given the data, it still looks reasonable, then hey, the fixed effects model was probably sufficient. I am unaware of a network study that we've done in the Odyssey community where the fixed effects model actually fits better than the random effects model, but I'm not, it could certainly happen. And so we should perhaps do a better job at that formal testing.
Thanks.
No problem. Slight practical overview. we're running the SOS challenge using Strategist. Strategist starts with a study design that Jack has very kindly provided us. Through the help of the community, we were able to take that study design and translate it into a single JSON specification file that makes it very convenient to share an entire reproducible study execution across the network. The way that we're currently sharing that is through GitHub, although one doesn't have to. There could be better mechanisms that will arise in the future. And this JSON gets ingested by a new package developed by Anthony Senna called Strategist. Strategist coordinates running the individual analyses that are specified within this JSON against each of our data sources against each of our CDMs in the data sources, and generates a number of output files which are conveniently stored as text files so that individuals like me as a data custodian can easily look through them and have a good idea of what I'm sharing to make sure I'm protecting patient privacy and rights. These CVS files are then shared, currently using secure FTP back to the study coordinator. The study coordinator uses a package called the results module, the results model manager, to upload all of the results across all of the different data sources to a single database against which our tools and individuals can query our results. And on top of this database is a Shiny app, which is kind of an easy way of querying the database if you want to get a gestalt feeling of what the results look like. However, when it comes to writing our final papers, I would suggest querying the database directly and not making screenshots from the Shiny app. You'll have a lot more control over what you want to present. Today, we're going to talk about sort of the evidence synthesis, which works very similarly after all the results have been added to the database. We're going to design our synthesis and then put that into a single JSON file. And that JSON file can also be ingested by Strategist to fit our evidence synthesis that we've discussed here. Let me stop. There was a question that just came up in the chat. We'll come back to that. Oh, sorry, Patrick's already taking care of the chat. Thank you, Patrick. Perfect. We'll come back to those. And then Strategist will give some output, again, some CVS files, which will display all of the results from our meta-analysis, which of course will be loaded up to our public results database and can be queried directly either for disseminating our evidence. So I'm going to walk through the steps of that JSON specification, which will be at the point to need that specification for the fluoroquinolone study very soon. There are a large number of individuals who have exposure to antibiotics, particularly fluoroquinolones, and so execution across a number of different data sources has been taking a little longer than we expected, but some expedient data sources like the VA have already finished. Patrick, have you guys finished in J&J yet?
You are much more expedient at the VA than I am at J&J.
Wow, that's a first. In order to do this, I added an R file, which is going to be the material that we're going over there with a little arrow towards it called evidence synthesis, if you want to play along. And of course, there's a link up here to the fluoroquinolone study. So we'll first talk about we need to create our analysis specification. And like we did for creating the JSON for the execution part of the study, there are a number of helper functions that are available in the evidence synthesis module. So if you just source those helper files, they'll be available for you. So we specify that we want to do evidence synthesis across all of our different sources, and we give it a source method, which currently the source method is implemented both for the cohort method and for self-controlled case series. In this case, we'll start with the cohort method. We need to define what type of approximation that we're using for our likelihood function. And in this case, the kind of best practices are use an adaptive grid. Then we need to provide a couple of options that specify the Bayesian model that we'd like to fit to these different likelihood functions. We need to give it a unique analysis ID so that it doesn't conflict with other results on the database server. We need to specify after calibration how we'd like our credible intervals calibrated. So this is interesting. We're starting with a Bayesian approach, and we're going to take posterior estimates from the Bayesian model and then apply calibration to assure that they have close to nominal frequentist or coverage properties under our calibration procedure. So I'm not quite sure I would describe this whole thing as a Bayesian technique or a frequentist technique. It's kind of an opportunistic one. So we'd like to return sort of confidence intervals that have approximately 95% coverage, assuming a type 1 error rate of 5%. And we're going to use our Bayesian random effects model. And of course, the source is going to come from the cohort methods that we had before. You can specify the same types of options for the self-controlled case series so that they don't conflict. I just gave it an analysis ID of 2. We generate a list of all of the analyses that we'd like to have, and basically say, given my list of different analyses, create the actual specification that we need to provide into our JSON file. Along with that specification, so create that specification and add in everything that this module additionally needs. Then you would just execute that. So that creates the JSON file. You could share that with somebody else who would be able to exactly reproduce your evidence synthesis of the data here. Our study coordinator, so Jack, this is going to be you. To execute it, you library up strategist, you connect yourself up to our Postgres database, which is holding all of the results behind data.odyssey.org. In good fashion, I'm not displaying passwords. I'm using keyring, which I'd like to encourage the rest of the community to get on board with so that we don't end up sharing private and personal information. And I point it towards where the results are and where I'd like the results to be on my computer when it's done. Store the connection details, set up all the execution details that need to be there, and then just hit execute. This will generate all of the underlying CVS files which have the metalytic answers themselves across data sources. I'd like at this point to take us to the data.odyssey.org results viewer for the fluoroquinolone study, but we're still busy. The gerbils inside of our computers are still running around their wheels, fitting these very large-scale propensity score models and extraordinarily large conditional Poisson models for our self-controlled case series. So not many of the data sources have finished yet, so the demonstration that we'll look at will be from the much smaller and less significant anti-VEGF study.
So Mark, just a quick question. I think it might be helpful, just to understand kind of maybe your experience on how long actually it took for the fluoroquinolone study, as you just mentioned, what scale are we talking about?
Okay. So there is. No. So that's.
Sorry, go ahead.
Jing, I understand your question and your pain as the custodian for open claims. There are some specification changes that you should probably change in your JSON file. So one of the things that happens when we fit the large-scale propensity score models is we use cross-validation to learn about how much regularization we want to put into that model. Generally, we use 10-fold cross-validation. and tenfold's a good way to go. But Cyclops by default wants to make sure you're really getting the right answer. So not only by default, yeah, well, I wrote it. I want to get the right answer. I want to make sure people get the right answer. I don't care if it takes infinite time. So not only does it do tenfold cross-validation, but it does it 10 times by default. So for very large databases for small data sets where you have a small number of individuals, there's a lot of stochastic error in doing number of folds and cross-validation, right? Because, one fold is like 3 people. So you do want to do it many times.
Yes,
if you have a million individuals, right? There's no reason why you have to do, right? yeah, you have the luxury of just doing it once. So one thing you probably want to do is start a separate computer, or maybe just be cavalier like I was in the VA and just hit stop, and go and go back and change all of your CV repetitions to 1.
Okay. Gotcha. Okay. I'll make don't
follow my advice. Don't be that cavalier.
I'll paste into the chat a specific line, Jing, where you could change it, because literally in the JSON specification, there's just one place where there's one value that's currently defaulted to 10, which you just delete a 0, and then you press go.
Okay, sounds good.
Yes, and that took cohort method in the VA, which is about 1/10 the size of open claims. 3 days.
Oh, that's not that.
Yeah, no, 3 days is totally fine, right?
That's okay. Yeah. That's okay. Okay, yeah, and another thing, I think. Oh, sorry. Go ahead.
Yeah, go ahead. Oh, I was gonna say, if 3 days is fine, just wait until I send you the next Legend Diabetes.
I shouldn't say that out loud too soon, right? But yeah, I think we have a Professor Sunfo from Peking University as well. So because we have Ingzhou data, and that data, I'll be very honest, like the server it's on, it's not that super powerful.
Performance, yes.
So we'll help test it out, kind of how we go by, like, if we run into any kind of memory issues or anything, we might also need to go into and check it out. But just want to mention that, because I think we had similar situation while running Legend and SOS earlier. But okay.
Also, something else to keep in mind. The slow part for cohort method is fitting the propensity score models. There aren't that many propensity score models, so that's a good thing. And we are capping the maximum number of individuals that you randomly sample for building that propensity score model. So it turns out, at least within the VA, the real rate limiting step was the self-controlled case series.
Okay.
And the self-controlled case series took about twice as long as the cohort method to execute.
Oh, okay.
And
we'll let you know how that goes with.
Yeah, let me know how that goes. The interesting thing about the self-controlled case series is, what originally got me engaged with OMOP was fitting self-controlled case series as quickly as possible. So it's actually nice to see now that it's the rate limiting step in some studies again.
Okay.
So just think about how bad that would be if before we had decided to make self-controlled case series a reasonable model to fit. Would have been even worse. But I wish you luck. I feel your pain. My heart's with you.
Okay, we'll test on a smaller data set first, just to see kind of how it goes, and we'll predict or we'll project how long it'll take. But we'll share on a rolling basis. And we have Professor Sun here. I think we'll kind of try simultaneously with Ingzhou data. Let's see how long that could take.
Yeah. So I'm going to look at very briefly the results that have been uploaded for a preliminary meta-analysis for the less significant study. As soon as data from the meta-analytic module gets put up into the database, the Shiny app recognizes what it is and puts out a tab called Meta currently. Meta is going to allow you to select between your different target and comparators that you're interested in looking at and the specific outcomes that you want, like most of the cohort method types approaches. And we'll start to give you the kind of the forest plot that you might expect. So within each of these 3 data sources where the results for VEGF have been uploaded, we have the calibrated best within data source. So this is using option 1 estimate for each of these data sources. And all of those likelihood profiles for the negative controls and for the outcomes were all shared. And that will give us our summary or our meta-analytic best estimate, which of course uses option 2 to control for the non-independence of confounding, which gives us our most probable effect estimate and a 95% credible interval, which has been calibrated to have approximately 95 of, a type 1 error rate of 5%. You get forest plots. Of course, if you're interested in the actual estimates themselves, they're up here. And you can look at similar results, which haven't been uploaded yet for the self-controlled case series. There are questions about the view. I mean, there isn't too much to the viewer, but are there questions that I can answer about that before we just kind of go on to general questions about evidence synthesis? No, it's all very self-explanatory, isn't it? Let me show you one.
Well, one thing I'd just like to reinforce about what you said there, Mark, and again, as a plea to all of you who have data and you're wondering, well, why should I participate? My data set's small or not going to provide very much. I think there's really high value in having a diverse network of databases that are participating. And what we have almost always seen is that there's value that comes from the idea of not just producing a composite estimate, but gaining confidence in the fact that we see consistency across databases, particularly given that we may be looking across claims and electronic health record data, across data from US and Europe and the Asia Pacific region. So the idea that multiple databases coming from different lenses of the healthcare system are producing evidence that seems to be compatible with one another gives us another route to understand things. And particularly for databases that are smaller, actually, yeah, you're pulling it up here, Mark, so I think it's actually a very useful exercise.
Here's your small database.
Yep,
right?
There it is.
It is providing information, right? This is, we need it. Without it, we kind of get the wrong answer, non-significance. With it, it's a significant estimate.
Yes. Yeah, so we really want to encourage you, and even if you are sitting there thinking, for those of you in Australia, thinking, well, our population is generally small and we won't contribute that much, you actually can contribute substantially to the overall story, not just qualitatively, but quantitatively.
Yeah, thank you, Patrick, for the very informative comments. That it reminds me why I need to participate with my data to this study, and Legend Diabetes too.
Sorry, I was also, I just in case you copy down, sorry, Patrick, I hate to do this. In case you copy down, Pat, the cross-validation, just a small typo in that.
I was purposeful in using the comma there because, Mark, we do have a couple other models in there that we're doing CV reputation equal to 1. And then we have the 1, 0. So if someone does a find and replace on 1, then they're gonna find that they're gonna put the 1 and the 1, 0 together.
Yeah. So search for quote 10 quote.
There you go. Yep, that'll work too.
Because there is a comma which separates it from the next command line argument. Great. Let me open the floor up in the case there are any other questions at the moment about about evidence synthesis or difficult or trouble that individuals are having with executing the study that we can address as a group. I suspect one person's trouble is going to be somebody else's as well.
Yes, since our data is located in the closed environment without internet access, I'm struggling to develop a Docker image for the study, and it took much more time I expected to get familiar with strategies. Stuff.
No, Chan, I understand your pain. You know, one of the data partners with whom I work with is within a firewalled environment where things, you know, kind of only go in. So I've been working on, I have a system which I don't like, but it works there. And it will work with the Docker image as well. And that is, you turn off the RANV cache so that, so it's making multiple copies of everything. Right. And then you populate all the dependencies. There are currently some bugs with Strategist when it tries to populate its dependencies. You actually physically have to open each of the modules and do RNV restore until it's clean.
That's what
So for the Docker image, that's difficult. But what you could do is you could do that on your own system, because this is what I do for the VA, and then make a zip out of the whole thing.
Right.
And then you could just copy that zip into the Docker container. The challenge I have is because symbolic links don't work that way and there's no cache, it is 1.8 gigabytes large, which isn't such a big issue, except the firewall that I have to go through opens up and examines each and every file within that. So it takes a couple of hours to go through. Not quite as bad for the Docker container, right? Because you just have to copy it once.
Right.
So that might be a way of handling it.
Yeah, similar. In the similar way, I think that I've just figured out how I can make that Docker image with the, as I just said, just with that zip file with the whole dependencies.
With all of the modules.
Right. Yeah. I've just figured out in this morning. It took much more time I've expected, but I've done. So I can share how we can do this.
Yeah.
Across the databases. Yeah,
that would be very helpful. And something that I'm working on so that those files aren't that large is how to actually use the symbolic links in RANV and a single cache. So it won't, even without the cache, it takes a couple hours to populate all the restore anyway. Yeah. Yes, J&J, thank you. We love Strategist. I'm being a little facetious. I have actually really grown to appreciate, almost even love, kind of the design. So there's another interesting feature in one of the data sources that I work with, in that they cannot instantiate directly the SQL that Circes converts JSON to. That SQL needs to be refactored. Well, that's actually really convenient now that Strategist has modularized everything. All I had to do, of course, after I figured out this, is make a new cohort generator module specific for this data partner that does that refactoring in that intermediate step. Now, every new study that they get, all they have to do is go to that JSON specification, and instead of pointing it to the usual cohort generator module, they can now point it to the one that does the refactoring for them. So that's exactly the modularity that Strategist was trying and has succeeded in bringing us, along with many other features that we're slowly removing. All right, that brings us up on time. There will be 2 sets of office hours. Martijn and Young are holding one on an East Asia, APAC inconvenient time, Thursday morning my time, and I'll be holding one Thursday afternoon my time, which is Friday morning for many of you. So I'll see you all on Friday. Happy Friday.